So we start the next lecture that is about principal component analysis. So in this first session, we will motivate the technique and see why we need it. Okay, so PCA belongs to the unsupervised learning class of algorithms in machine learning. And the reason is that we have a number of observations, vector observations, from x1 to xp because we have p observations, but we don't have associated labels. For instance, here we have two observations made of two components. The first one is temperature, the other one is a filtered electricity load. So for instance, what is the fluctuation around the mean? And so this fluctuation can be positive or negative. And what we see here is that there are two different kind of behaviors. So we have this behavior here on the right if the weather is hot, and this behavior here on the left when the weather is cold. So PCA will try to capture these trends, underlying trends in the data. So let's say that we have here we have temperature, but actually we don't have a single temperature measurement. We have 200 temperature measurements. So can we summarize all those measurements onto just one or two or three variables describing the temperature? That is the task of PCA. So PCA is also used to determine linear combinations of the input variables that can be used to summarize the data without losing much information. And this information will be quantified through the concept of variability. So we want to have as few variables as possible that explain as much of the variability as possible. And then this is also used as a summary when you have a large set of correlated variables. So you can imagine that these 200 weather stations, they are very much correlated to each other because they record similar information. So this PCA is used to find explanatory variables, so summary variables. They're also used in regression or clustering or forecasting when the number of variables is high and or the variables are correlated. Also, the PCA components themselves can be patterns that we can try to explain in the data. And in any case, PCA will be capable of reducing the amount of variables without losing much of the variability. Okay, so let's see some example. This is a synthetic example where we simulate the data. So what we have are two signs and a sign that is a little bit shifted, and then we always have noise. And x1 and x3 they are signs, but one is bigger than the other, and this is the plot how it looks like. So this would be t in time, that is measured in radians, and then this is the aspect of x1, x2, x3 in this plot. Okay, so we can measure the correlation matrix between the three variables. So we know how to compute the covariance, and from the covariance the correlation matrix. So here is how the scatter plots between pairs of variables look like. And we see that between x1 and x3 there is a very strong correlation, and the reason is clear because both are signs plus some noise, and it is the same underlying signal. so that is why the correlation is so high. And the other x2 is almost the same sign. It is not exactly the same sign because it has been shifted by 0.1 pi, but it is almost the same. So we can let's look for some summary of this information. So the three signals have kind of the same information. So they have maxima, minima, they are all periodic with period 2 pi, and the maximum is around pi half, the minimum is around 3 pi half, and then at 0 pi and 2 pi they are almost 0. So just an average of all these three signals would be a good summary of the three. So here we have the average of the three, so it is plotted in black, and what we see is that just the mean summarizes more or less the content of the three signals. Okay, so here we have box plot signals for box plot measures for each one of the x1, x2, x3 signals, and for the summary and for the mean, and we see that the mean itself doesn't lose too much information with respect to the previous ones, to the original variables. So we can plot where the mean is. So the mean, so let's say that we have all this information. These are so every point is a point from the original plot. So at a particular time we have this x3, this x2, this x1. So if we take pairs of x1, x2, then this is how they look like. So every point represents a time point in the original plot. Okay, so we can compute what is the center, so what is the 0, 0 point, and that has been shown in red. And then we have the mean, so between x1 and x2, the mean, so we are proposing the mean to be x1 plus x2 plus x3 divided by 3. So just for a moment, let's forget that we have three variables. Let's pretend that we have only two. So the mean would be x1 plus x2 divided by 2. That is this green line. So what we are doing by summarizing the data by approximating by this line is just projecting each one of these points onto this green line, or substituting every one of these points by the corresponding point in the green line. So these are these projections ideas. So we have an observation, and this observation is projected onto the line. So calculating the mean, that is x1 plus x2 divided by 2, is projecting a point onto a line. Then we can go further in this idea of projections. So for that we need to define the scalar product between two vectors, and the scalar product between u and v is defined as in the standard Euclidean dot product. It is u transpose v, and it is the same. So u dot product v is the same as v dot product u, and it is defined as this thing. So it is the addition of all the component-wise multiplications. And then we can also define the angle between two vectors. So it is the dot product between u and v divided by the norm of u and the norm of v. And the norm, it is not defined here in the slide, but you know that it is the square root of the dot product of a vector to itself. Okay, so now we can define also the if we have a vector u that we are projecting onto a vector v, so what we have to do is to find a point along v such that the angle between, if we take that point and we join it with u, the angle between v and this other segment is 90 degrees. So this point here is we have to multiply u times or dot product with the normalized v. So you can see we have v divided by the normal v, so that is the unit vector in the direction of v, and then it is the dot product. So this vector, this point here is, or the length is the dot product between u and the unit v vector. Okay, so here we have a couple of examples where we have the same u vector, but v is different. They have the same direction. So this is 0.1, 0.1, this is 0.5, 0.5, so it is the same vector or the same direction but different, described with a different vector. And what we can see is that the projection that we defined before of u onto v is in both cases is the same, so it is 0.18. So this 0.18 is the length of this segment here. So you take u, you project it onto v, and then this length is 0.18. Okay, so here we have the projections of each one of these points onto the direction defined by the green line. The green line was 0.5, 0.5. Okay, so here we have what is the mean, this is what is the projection. So the projection and the mean, they're very much linked to each other. So actually the mean, if we divide by the 0.71, that 0.71 is the unit norm, or it is the norm of v, then we have exactly the projection. So computing the projection and computing the mean is almost the same. Okay, so we had an example in which we had these data points in 3 variables, x1, x2, x3. So now instead of having instead of having 2 components as we had here, x1, x2, we have 3. So now the average will be x1 plus x2 plus x3 divided by 3. So this is now this green line, this is the 0, 0 point, 0, 0, 0. And it could be that the mean is a good summary of the data, as it happens in this x1, x2, x3 example, but it might be that it is not, like in this one. There are several trends here. So let's see if we can find another way of finding summaries. So here we have another example. So in this example, now x1 and x3 are signs as before, but now x2 is a sign that is 180 degrees apart from the previous one. So there is a phase shift of 180 degrees. So the correlation now between x1 and x3 is high because both are signs, and the reason why it is not as high as before is because there is much more noise, and then the correlation between the 2 variables degrades. But then x2 is negatively correlated to the other two variables, to x1 and x3. We can see it here. So x1 and x3, they follow the same sign pattern, while x2 is just the opposite. So that is why we get this very negative correlation. Okay, so now if we do the same trick as before, so just computing the average of the three to construct the summary, what we see is that the summary does not reflect. So the summary is almost zero everywhere except for the noise. So it does not reflect really the variability of the input data. So what we need to find some other way to summarize. So here we have represented in the scatter plots between x1 and x2, x1 and x3, we have represented the average, so taking the average. So this taking the average in x1, x3 would be a good idea, because they go with the data, with a cloud of data points. But in the plain x1, x2 or x2, x3, they go just in the perpendicular direction to where the data is going. So this is not really a good summary. And just a reminder, so when we have a cloud of points, and we are showing it in 2D, but it applies to more dimensions, the covariance matrix defines the direction in which the data is varying. So for instance, let's say that we have a diagonal covariance matrix, so the off-diagonal terms are almost zero. So that would mean that this data cloud is aligned or is made of independent components. So x1 and x2, they are independent from each other, and the diagonal terms tell us the relative variability. So x1 has much larger variability than x2, and this is the case here. So we have x1 here with more variability than x2, and x1 and x2 are independent from each other. But now if the data, if x1 and x2 become correlated, then the off diagonal terms are not zero anymore. They have some positive or negative correlation, and the diagonal terms, they don't contain any longer the variability of x1 and x2 independently, but somehow they are intermixed. And if we want to recover the variability of x1 and x2, or this x1 prime that goes in this direction and x2 prime that goes in this direction, then what we need is to compute the eigenvalues of the covariance matrix. Okay, so now we can rotate, we can, given a pair of points x1 and x2, we can always find a rotation of those 2 points, of those 2 variables, so that the covariance matrix has the properties that we want. So let's say that our original data has this pattern, so we can always rotate x1 and x2 to construct new variables y1 and y2, such that y1 and y2 have this shape or this shape or this shape. So this is what we are doing here. So let's say that we have 2 input variables x1 and x2, we multiply by a rotation matrix, and then we have y1, y2. So x1 and x2 have this plot, y1, y2, we want it to have this other plot in this new set of variables. Yeah. Okay, so if the covariance matrix if the input covariance matrix in the X space is this one, it can be shown that if y is constructed in this way, that is multiplying x by a matrix, and then this matrix, this new set of y variables, if this matrix is orthonormal, then the covariance matrix of this is W times the covariance matrix of X times W transpose. And then we can make, for instance, this one, where we can make the off-diagonal terms to be much smaller than, or to be smaller at least. And we can find the rotation, the exact rotation that makes y1 and y2 to be independent from each other. And to do that, what we can do is to decompose x, or the covariance of x, into eigenvalues and eigenvectors. So if we do the eigendecomposition of the covariance matrix, lambda, that is a diagonal matrix, so that means that in this rotation indicated by the matrix A, the components, the new variables, will be independent from each other, because the remaining matrix will be diagonal. So this is at the core of PCA. So we will see it later in more detail, but the core of PCA is finding a rotation such that the covariance matrix of the newly constructed variables is diagonal. And PCA finds a lot of uses, and this is one a relatively interesting example in which we measure a lot of variables regarding what are the distances between key points in your phase, and we keep distances, angles, and then with all this set of variables we construct a PCA, and from this PCA your phase typically is uniquely determined in that PCA space. So this is a kind of biometric characterization of a person, and then we can uniquely identify that person. So that is like the identity card of that person, and PCA is used for that. Okay, so let's stop here, and we will see more details about the PCA in the next session.